Ladies and gentlemen, I am Dr. Ming-Shin Kuo, an associate professor in the bachelor program of Artificial Intelligence Technology and Innovative Design at Tainan University in Taiwan. The topic of my research is a novel fuzzy gray-based possibility theory, soft computing process for pest control method selection. Now, I will explain the key points of this study and its conclusions. Introduction. Ceratoma papulosa, also known as the lychee stink bug, is a major agricultural pest in Taiwan. This insect, originally found in China and Southeast Asia, has become a significant threat to Taiwan's longan and lychee crops. These crops are crucial for the local economy, and the damage caused by this pest affects not only the quantity of the harvest, but also the quality of the fruits, making them less marketable. The problem posed by Ceratoma papulosa is twofold. First, it directly impacts agricultural production by reducing crop yields and quality. Second, it poses a potential health risk to those who come into contact with the pest, as it secretes toxic liquids that can irritate the skin and eyes. This dual threat underscores the urgency of finding effective pest control solutions. Our objective in this research is to develop a method for selecting the most effective pest control strategies, particularly under the uncertain and fuzzy conditions that often characterize agricultural decisions. Traditional methods may not fully capture the complexities of this problem, so our approach aims to provide a more sophisticated and reliable solution that benefits both the agricultural industry and public health. Pest control methods. In Taiwan, several pest control methods are used to manage the Ceratoma papulosa, each with its advantages and challenges. Physical methods. This approach includes manual techniques such as shaking or tapping the branches of lychee and longan trees to dislodge the bugs, which are then collected and destroyed. While this method can be effective for small-scale operations, it is labor-intensive and not practical for large orchards. Biological methods. Biological control involves using natural predators of Ceratoma papulosa, such as the parasitoid wasp Anastatus formosanus, which parasitizes the eggs of the stink bug. This method is environmentally friendly and sustainable, but its effectiveness can be limited by environmental factors and the need for precise timing. Chemical methods. The use of chemical pesticides, such as thiacloprid and cyalothrin, is a common approach. These pesticides are sprayed to control the infestation, particularly during critical periods like flowering. However, chemical control comes with significant concerns, including the risk of pesticide residue on fruits, which can pose health risks to consumers and impact export markets. Challenges. Despite the availability of various pest control methods, several challenges remain in effectively managing Ceratoma papulosa. Pesticide residue. One of the most pressing concerns is the residue left by chemical pesticides on fruits. This not only raises food safety issues, but also affects the marketability of the, particularly in markets with strict pesticide regulations. Environmental impact. The excessive use of chemical pesticides can lead to environmental degradation, harming non-target species, including beneficial insects like pollinators. This can disrupt the ecological balance and reduce biodiversity. Need for integrated pest management, IPM. There is a growing recognition of the need for integrated pest management, IPM, strategies that combine multiple methods to reduce reliance on chemical pesticides. IPM emphasizes sustainable approaches, including the use of biological controls and precise application of chemicals only when necessary. However, implementing IPM effectively requires careful planning, monitoring, and the integration of different control methods. In this section, I will explain our methodology, focusing on three key components: multi-criteria decision-making, MICDEM, fuzzy gray and possibility theory, and the mathematical model. MICDEM allows us to evaluate various pest control methods by considering multiple factors like effectiveness and environmental impact. Fuzzy gray possibility theory help handle uncertainty and imprecision, enhancing the robustness of our decision-making process. Our mathematical model combines these techniques within an NZM framework to rank alternatives and select the best pest control strategy. Together, these components provide a comprehensive approach to making informed and sustainable pest control decisions. Multi-criteria decision-making (CDM) is an essential tool in decision science, especially when dealing with complex environments, where multiple, often conflicting criteria must be considered. In many real-world scenarios, decision-makers face the challenge of balance factors that can impact the outcome. For example, in the context of pest control, different stakeholders, including farmers, environmentalists, policymakers, and consumers, have varying priorities. Farmers may prioritize cost-effectiveness and yield, while environmentalists focus on sustainability and minimizing ecological damage. Consumers, on the other hand, are increasingly concerned about food safety and the presence of pesticide residues. McDM provides a structured approach to systematically evaluate and compare various pest control methods by taking into account all these factors simultaneously. It allows for the integration of both quantitative data, such as the cost of pesticide application, and qualitative assessments, such as the environmental impact or the social acceptance of a particular method. By weighing these factors according to their importance, McDM helps to identify the most balanced and effective pest control strategy. Moreover, McDM is not just about choosing the best alternative based on current conditions. It also facilitates scenario analysis, allowing decision makers to understand how changes in one criterion, like an increase in pesticide regulation, might affect the overall decision. This flexibility makes McDM a powerful tool for making informed, balanced decisions that reflect the needs and values of all stakeholders involved, ensuring that the chosen solution is not only effective, but also sustainable and socially responsible. In the table below, it can be observed that in past fuzzy McDM research, although these methods address McDM problems in a fuzzy environment, only some of them incorporate the concepts of positive ideal points and negative ideal points to solve McDM problems. Additionally, some methods consider the complexities of risk in the decision-making process. However, very few fuzzy McDM methods simultaneously take into account both the concepts of positive and negative ideal points and the complexities of risk in the decision-making process. Therefore, this study aims to develop a new fuzzy McDM approach that simultaneously considers both of these concepts and methods. Fuzzy array and possibility theory. Traditional multi-criteria decision-making (McDM) methods often face challenges when dealing with uncertainty and imprecision, which are common in real-world scenarios like pest control. To overcome these challenges, we integrate fuzzy gray relational analysis (GRAE) and possibility theory into our methodology. Fuzzy gray relational analysis (GRAE), as defined by Kuo 2011, is particularly useful in dealing with the imprecise nature of the data. Fuzzy array allows for a more flexible comparison between alternatives by assessing the degree of similarity between them. This method uses fuzzy numbers to represent uncertain or imprecise data, enabling decision makers to capture the nuances in the comparisons between different pest control strategies. For example, when evaluating the environmental impact of two pesticides, fuzzy array helps to determine how closely each method aligns with the ideal outcome, even when exact measurements are difficult to obtain. Possibility theory, as outlined by Zhang et al. 2009, provides a robust framework for managing uncertainty by modeling the potential outcomes of decisions in a way that reflects the inherent vagueness and ambiguity of the data. Unlike traditional probabilistic approaches, which require precise probabilities, possibility theory allows for a range of possible outcomes, each with its degree of possibility. Zhang et al. 27. Define the possibilistic mean value and possibilistic variance to represent the expected value and the stability of the information, respectively. These concepts are essential for evaluating the risk associated with each pest control method, as they allow decision makers to account for both the expected performance and the variability in outcomes. In practical terms, possibility theory enables us to assess the range of potential impacts of a pest control method, even when the exact effects are not fully known. For instance, if the long-term environmental impact of a pesticide is uncertain, possibility theory allows us to model this uncertainty and incorporate it into the decision-making process. By integrating fuzzy GRA and possibility theory, our methodology enhances the robustness and flexibility of the decision-making process. This combined approach allows us to evaluate pest control strategies more effectively, considering both the precise and imprecise aspects of the data, as well as the uncertainties inherent in real-world scenarios. The result is a more comprehensive evaluation that helps identify the best pest control strategies, balancing effectiveness with risk and ensuring that the chosen method is both practical and sustainable under varying conditions. Next, we will explain the mathematical model. The computational process, steps, and definitions for the fuzzy McDM approach based on the possibility theory proposed in this study are outlined as follows. Step 1. Identify a set of criteria for the assessment or selection issue. Step 2. Denote the importance weights and ratings using appropriate linguistic terms. For the definitions of importance weight and ratings, we use linguistic terms as illustrated in the two sample tables. Next, step 3. Aggregate the fuzzy weights with the fuzzy ratings. We will calculate the average fuzzy weights and fuzzy ratings for all decision makers. Step 4. After calculating the average fuzzy weights and fuzzy ratings, we then construct two matrices, the fuzzy decision matrix and the fuzzy normalized decision matrix. Step 5. Define the positive ideal points and negative ideal points. Step 6. We construct the following decision matrices: the positive ideal fuzzy normalized decision matrix, the negative ideal fuzzy normalized decision matrix, the positive ideal weighted fuzzy normalized decision matrix, and the negative ideal weighted fuzzy normalized decision matrix. Step 7. The positive ideal possibilistic mean value matrix, negative ideal possibilistic mean value matrix, positive ideal weighted possibilistic mean value matrix, negative ideal weighted possibilistic mean value matrix can be constructed. Step 8. We can obtain the possibilistic standard deviation matrix of positive ideal, negative ideal, positive ideal weighted, and negative ideal weighted. Step 9. We calculate the weighted fuzzy gray relational coefficient of possibilistic mean values, WFGPM, among ideal with negative ideal alternatives and compared alternatives. Step 10. We calculate weighted fuzzy gray relational coefficient values of standard deviation, WFZ-SD, among ideal with negative ideal alternatives and compared alternatives right. Step 11. We can obtain close relationship values of integrated relative closeness coefficient. Step 12. Based on the CR value, the decision marking finds the best alternative. The larger the CR value, the more favorable the alternative is considered. To evaluate the pest control methods effectively, we identified 6 key criteria: efficacy, environmental impact, safety, cost, compatibility with integrated pest management, IPM, and practicality. Each criterion plays a crucial role in determining the overall suitability of a method for sustainable pest management. Through a survey of agricultural experts, farmers, and government officials, we determined the relative importance of each criterion. Efficacy and safety emerged as top priorities across all groups, while cost and practicality were especially important to farmers. This stakeholder input guided our evaluation process, ensuring that the final assessment aligns with real-world needs and challenges. 5 pest control methods. 1. Manually shake or tap lychee branches to dislodge and eliminate adult insects. 2. Release Anastatis formosanus to parasitize Tesseraktoma papilosa eggs as a biological control method. 3. Manually spray pesticides like thiacloprid, phyllothrin to control infestations. 4. Use UAVs with AI-based UNet technology to precisely detect Tesseraktoma papilosa eggs, allowing targeted release of Anastatis formosanus. 5. UAVs with UNet technology also detect adult insects for accurate pesticide application. Based on the proposed fuzzy McDM approach, we evaluated and ranked 5 different pest control methods for Tesseraktoma papilosa. The methods were assessed using the 6 criteria we previously defined: efficacy, environmental impact, safety, cost, compatibility with integrated pest management (IPM), and practicality. Our evaluation ranked 5 pest control methods using our proposed fuzzy McDM approach. The UAV-assisted biological control method was identified as the best overall, followed by UAV-assisted chemical control. These top methods demonstrated superior performance across most criteria, particularly in efficacy and environmental impact. The UAV-assisted biological control method was the top performer, excelling in efficacy, environmental impact, and safety. The UAV-assisted chemical control method also performed well, particularly in terms of precision and effectiveness, though it faced some challenges related to environmental impact. The results of the sensitivity analysis revealed that the proposed method demonstrated high stability across various resolving coefficients. The top-ranked methods, particularly UAV-assisted biological control and UAV-assisted chemical control, consistently maintained their positions, regardless of changes in the criteria weights. This consistency indicates that our approach is reliable and robust, providing confidence in the validity of the rankings. Our sensitivity analysis confirmed the stability of the rankings produced by the proposed fuzzy McDM approach. Even with significant variations in resolving coefficients, the top methods, including UAV-assisted biological control, maintained their positions, demonstrating the robustness and reliability of our evaluation. This study introduced a novel fuzzy McDM approach using possibility theory to select the best pest control methods for Tesseraktoma papilosa by integrating positive and negative ideal points with risk considerations. We identified UAV-assisted biological and chemical control as the most effective strategies. The method proved reliable and stable under various conditions, demonstrating its potential for real-world agricultural application. Future research could apply this fuzzy McDM method to other agricultural challenges and pests, with further refinement incorporating advanced AI techniques for improved precision. Adding criteria and exploring new weighting methods could enhance the model's accuracy. Field trials to validate the model's recommendations would support broader adoption in real-world settings. This concludes my presentation. Thank you all for your attention.